Hello everyone and welcome back to our channel. Today, we're diving deep into a topic that's fascinating, alarming, and critically important. The gaping hole in the ozone layer over Antarctica, which is now the size of North America. We're not just scratching the surface. We're going to unravel the theories that have been put forth to explain it and explore the mind-boggling implications it can have on our world. But we won't stop there. We're going to zone in on the specific implications of heightened UVC radiation. It's critical to understand how it can impact our health, ecosystems, and the very fabric of our society. To start things off, let's delve into the startling discovery of the massive ozone hole in Antarctica. According to recent satellite data, this year's ozone hole has reached unprecedented proportions. It measures approximately twice the size of the entire continent itself. Now, you might be wondering, what exactly is the ozone layer and why is it so crucial for our planet? The ozone layer is a vital component of Earth's atmosphere that shields us from harmful ultraviolet rays emitted by the sun. This protection is essential for safeguarding human health and preventing the harmful effects of UV radiation such as skin cancer, cataracts, and sunburn. Beyond shielding us from harmful ultraviolet rays, the ozone layer has other crucial functions including preservation of ecosystems. The ozone layer plays a crucial role in safeguarding terrestrial and aquatic ecosystems. It protects phytoplankton, which is responsible for producing a significant portion of the world's oxygen and serves as the foundation of marine food chains. Additionally, it helps maintain the health of forests, which are essential for carbon sequestration and biodiversity. Agricultural benefits. The ozone layer helps protect crops from excessive UV radiation. Overexposure to UV rays can harm crops and reduce agricultural productivity. By maintaining the ozone layer, we ensure that our food sources remain resilient and abundant. Prevention of climate change. While the ozone layer itself isn't a direct contributor to preventing climate change, its protection of phytoplankton and forests indirectly aids in carbon sequestration. Healthy ecosystems play a role in mitigating the effects of climate change by absorbing carbon dioxide from the atmosphere. Weather and climate regulation. Ozone in the stratosphere influences atmospheric temperature and circulation patterns. By maintaining these patterns, the ozone layer helps regulate weather and climate, ensuring that they remain relatively stable. Technology and communication. The ozone layer also influences the propagation of electromagnetic waves, which are essential for various technologies like radio and satellite communication systems. Maintaining the ozone layer ensures the reliability and efficiency of these technologies. In the 1980s, the scientific community discovered that human activities, particularly the use of chlorofluorocarbons, CFCs, in products like aerosol sprays and refrigerants, were depleting the ozone layer. The discovery of ozone layer depletion led to a global ban on CFCs in 1989 under the Montreal Protocol. This international agreement aimed at safeguarding the ozone layer. While we've made significant progress in reducing ozone-depleting substances, challenges still persist. Now, let's dig deeper into the story. In the early months of 2022, an underwater volcano in Tonga erupted, unleashing a significant volume of water vapor into the upper atmosphere. Scientists believe this was crucial, and this water vapor was in the creation of this massive ozone hole. This year, the ozone hole above Antarctica reached its maximum size on September 16th, covering an area equivalent to North America or supposedly twice the size of Antarctica itself. It's clear that the eruption of the Tonga volcano created favorable conditions for the formation of polar stratospheric clouds, which are crucial to ozone depletion. While the eruption of Tonga's underwater volcano has been a key focus, there are alternative theories worth exploring. These theories highlight the intricate web of factors that could have contributed to the expansion of the ozone hole. So let's dive right in. Our first theory takes us beyond Tonga. While the eruption of Tonga's underwater volcano is a prime suspect, what if it's not the only player? Could other volcanic eruptions elsewhere on the planet have collectively injected substantial aerosols and water vapor into the stratosphere? The combined impact of multiple eruptions might have played a role in the ozone hole's expansion. Now, let's turn our attention skyward. Solar variability is another intriguing theory. Variations in solar activity, like fluctuations in solar radiation and solar flares, can influence the Earth's upper atmosphere. A prolonged period of increased solar output or an unusual solar event could potentially impact ozone depletion, potentially contributing to the observed anomaly. Our third theory zooms in on atmospheric trends. Changes in long-term stratospheric water vapor trends could be key. An increase in water vapor levels in the upper atmosphere due to natural climate variability or alterations in atmospheric circulation patterns might have had a hand in expanding the ozone hole. From trends, we shift to pollutants. It's not just natural events that could have influenced the ozone hole. Air pollution and anthropogenic aerosols, even in regions far from Antarctica, can have far-reaching atmospheric effects. The long-range transport of these pollutants to polar regions might have indirectly impacted the ozone layer's chemistry. Unique atmospheric conditions. Rare and atypical atmospheric patterns in the southern polar region could have favored the ozone hole's expansion. Think of these conditions as intricate puzzles like unique air circulation patterns, temperature inversions, or atmospheric wave dynamics. Altered temperature profiles, shifts in atmospheric circulation, and other climate-related factors might interact in ways that lead to larger ozone holes. In conclusion, the size of the ozone hole above Antarctica is a puzzle with multiple pieces, each representing a complex, interconnected factor. While the eruption of Tonga's underwater volcano is a significant contributor, these alternative theories show that the story is far from one-dimensional. Individual theories can impact other theories. They can all be interrelated. Our understanding of these dynamics is continually evolving, and comprehensive research and ongoing monitoring are vital for unraveling this complex puzzle and for preserving the ozone layer's integrity. Now, let's dive into the scariest part of the story, the potential implications of a hole this size. Brace yourself as we explore a series of deeply alarming scenarios that could result from this environmental catastrophe. UV radiation. First, a gaping hole in the ozone layer means heightened UVC radiation. As mentioned in one of our previous videos, UVC radiation is reaching the Earth contrary to what many believe. It has been tested and found to have been hitting Earth's surface for many years now. When we have a larger ozone hole, it allows more UVC radiation to penetrate the Earth's surface. UVC radiation is the most potent and potentially harmful type of UV radiation, especially for those at higher risks for certain cancers. It's so powerful that it can break molecular bonds, leading to genetic mutations. The increased exposure to UVC radiation would have dire consequences for public health. Skin cancer rates would soar, with a significant increase in melanoma and non-melanoma skin cancers. The strain on healthcare systems would be immense, as the demand for treatment and preventative measures like sunscreen and protective clothing would skyrocket. Moreover, the prevalence of cataracts would surge, potentially leading to a higher incidence of blindness and the need for costly surgical interventions. The sheer volume of cases could overwhelm healthcare infrastructure, particularly in regions with limited access to medical care. Treatment would place an immense burden on healthcare systems and resources, potentially resulting in a scarcity of healthcare personnel, oncology drugs, and radiation therapy equipment. Patients might face extended waiting times for treatment, which, in turn, could lead to a higher mortality rate. People would live in constant fear of skin damage and cancer, altering daily life and causing psychological distress on a global scale. Ecosystem collapse. The disruption to Antarctic ecosystems would be profound. Phytoplankton, which is responsible for producing a significant portion of the world's oxygen and is a primary food source for marine life, would be severely affected. A collapse in phytoplankton populations could disrupt the entire marine food chain, impacting species such as krill, fish, and even marine mammals like seals and whales. This could lead to mass die-offs, triggering ecological imbalances with far-reaching consequences for biodiversity and fisheries worldwide. Global food shortages and famine. Crop failures due to the harmful effects of increased UVC radiation could cause a global agricultural catastrophe. Food production would decline significantly, leading to food shortages and, in some regions, famine. Staple crops like wheat, rice, and corn could see reduced yields, driving up food prices and increasing the risk of malnutrition in vulnerable populations. This could spark food-related conflicts and unrest, further straining international relations. Desperation and competition for limited food resources could lead to widespread civil unrest and potential conflicts over access to food supplies. Accelerated ice melt. The intensification of ice melt in Antarctica could have catastrophic consequences for coastal regions around the world. Sea level rise would occur at a faster rate than previously anticipated, leading to the inundation of coastal cities, displacement of millions, and the loss of valuable coastal property. Governments would face immense challenges in planning for and managing mass migration, while global economic centers would be threatened by the prospect of damage to critical infrastructure. Entire coastal communities would be forced to relocate, posing logistical and humanitarian challenges of unprecedented proportions. This mass migration could result in overcrowded refugee camps and conflict over available resources, leading to a destabilizing global crisis. Extreme weather events. The alteration of atmospheric circulation patterns and a disrupted jet stream due to the massive ozone hole could result in unpredictable and more severe weather events. Coastal regions might be battered by more intense storms, while other areas could experience prolonged droughts and heat waves. This unpredictability would place additional pressure on emergency response systems and infrastructure, increasing the risk of catastrophic weather-related disasters. The catastrophic impacts of an enormous ozone hole could push ecosystems and environmental systems to tipping points where they may undergo irreversible changes. Coral reefs might bleach and die, and fragile ecosystems like the Amazon rainforest could become more susceptible to droughts and fires, releasing vast quantities of carbon into the atmosphere, exacerbating climate change and further destabilizing ecosystems. Technological challenges. The need to protect technology and infrastructure from extreme UV radiation would become a significant technological and financial challenge. Space-based assets, such as satellites and space stations, would require enhanced shielding, and the cost of building and maintaining these technologies would increase substantially. This could affect global telecommunications, weather forecasting, satellite communication, and global positioning systems and scientific research. Protecting technology and infrastructure from extreme UV radiation would become a monumental challenge. Social disruption. As the cumulative effects of these consequences unfold, social unrest could become more common. Protests, riots, and political instability could arise in response to failing infrastructure, food shortages, and a heightened sense of insecurity. Governments would face increased demands for action and the need to manage social upheaval. Policy and governance challenges. The scale of these challenges would necessitate rapid policy and governance responses. Governments would need to implement emergency measures to protect public health, stabilize food supplies, and adapt to shifting climate patterns. International organizations would face the task of coordinating global responses to crises. The need for revised international agreements and climate policies would become increasingly urgent as the world grapples with the daunting implications of a gaping hole in the Antarctic ozone layer. Competition for resources. Conflicts over resources, including water and arable land, could escalate into full-scale conflicts, potentially leading to regional and global warfare. In conclusion, the implications of a gaping hole the size of North America in the Antarctic ozone layer are nothing short of terrifying. These scenarios are a stark reminder of the urgency of preserving the ozone layer and the need for immediate and coordinated global action to mitigate the potential consequences of further ozone depletion. Before you go, we'd love to hear from you in the comments. We appreciate your support with a like, and we encourage you to hit that subscribe button if you found today's video interesting. All things considered, this is just another alternative notion. Thank you for watching.